Good day to our IGS community members around the globe. On behalf of the entire Central Bureau staff, it is my pleasure to join you virtually today to discuss recent progress in implementing the 2021+ IGS Strategic Plan, including 2 use cases illustrating the Central Bureau's work towards incubation of novel applications and advocating the value of geodesy to the public. For almost 30 years, the International Global Navigation Satellite System Service, or IGS, has carried out its mission to advocate for and provide freely and openly available high-precision GNSS data and products. We are an entirely voluntary federation of organizations around the world, working together to achieve advances in geodesy that would be impossible without international collaboration. As it enters its second quarter century, the IGS is evolving into a truly multi-GNSS service, and at its heart is a strong culture of sharing expertise, infrastructure, and other resources for the purpose of encouraging global best practices for developing and delivering GNSS data and products all over the world. The IGS portfolio of products is constantly evolving and growing. This presentation will be supported by 2 use cases highlighting the atmospheric part of our organization's work, including the ionosphere and troposphere. As we look to the future of the IGS, we are guided by the most recent strategic plans, goals, and objectives. The IGS 2021+ Strategic Plan was developed by the IGS Governing Board with the help and support of the Central Bureau and guided by extensive community feedback and discussions. It presents a forward-looking strategy addressing the role of IGS as facilitator, incubator, coordinator, and advocate, working towards 3 major goals in service to our community and beyond. Central to the goals and objectives are complementary roles of the IGS as a collaborative research program, as well as an operational service. Last 2 years, the IGS Central Bureau has been identifying these advocacy opportunities and incubating preliminary research for the benefit of our geodetic community, as well as science and society. As you will see later in the presentation, these research innovations have direct applications to major international frameworks and could eventually form concrete and highly visible contributions of geodesy to social well-being and disaster risk reduction. These 2 use cases utilize novel applications and unanticipated benefits of GNSS data and products for advocating the importance of geodesy in an ever-expanding suite of applications. In this case, understanding and modeling 2 types of disaster risk: tsunami and wildfires. I will now give the virtual floor to my colleagues Leo Martire and Mayra Oyola-Merced to explain more about their research in these sectors. Thank you.
Thank you, Allison. I am Leo Martire, and I'll be talking about GNSS-Enhanced natural hazards early warning systems through near real-time ionospheric monitoring. On this first slide, let me acknowledge my co-authors, without whom this presentation will not have been possible. First, to give a little bit of background, all natural hazards will generate atmospheric waves. Those atmospheric waves will propagate up to the ionosphere, where they will cause fluctuations in electron densities, as is displayed on the schematic on the top right of this slide. Perturbations in the total electronic current, TEC or TEC for short, can be detected using GNSS observations between a GNSS satellite and a GNSS ground receiver. Our objective is to use real-time GNSS-derived data to augment natural hazards warning systems. As you can see on the movie on the bottom right here, for the case of the Tohoku Oki event, ionospheric perturbations are clear following the earthquake and tsunami during that day. In terms of spatial coverage, this type of GNSS monitoring relies on satellites and ground stations. In terms of satellites, we already have multiple satellite constellations deployed, for example Baidu, Galileo, GLONASS, and GPS. In terms of ground stations, there exist more than 6,000 public stations available through different agencies, including 200 more or less GGPS stations streaming data in real time. In the remainder of this presentation, I will use the 2022 Tonga eruption, which occurred in the Kingdom of Tonga, as displayed on the map on the bottom right of this slide. It is important to note that multi-GNSS tracking allows a better coverage for TEC perturbations, and simple signal processing methods are sufficient to distinguish those signals. In the bottom plot on the left-hand side, I will show data related to the Tonga eruption. On the left-hand side, I plot GPS TEC data as a function of distance to the eruption on the vertical axis and time on the horizontal axis. And you can already see perturbations at the scale of about 2 TEC units. On the middle plot here, this is a sort of sky plot, plotting the path of the satellite that are being tracked by the station FTNA as a function of azimuth around the circle and distance to the station radially. If we add to those plots GLONASS data, we see that we increase the amount of data available as well as the coverage of the sky above the station. In short, a key point is that a single ground-based GNSS station is sufficient to capture the key signals of interest up to a distance of about 1,200 kilometers away. Still focusing on the Tonga eruption, I will now show a video highlighting the ionospheric disturbances following a volcanic eruption. The background, here in pink, represent a global ionospheric map, and the foreground, all those dots, represent TEC data filtered for periods shorter than 60 minutes. As we play the movie, we will see in the background an ionospheric depletion shortly after the eruption, as well as strong perturbations in the TEC data emanating from the volcano. Shortly after that, we will see the main wave traveling over New Zealand to the south, and then a little bit later than that, we will see an enhanced ionospheric activity over eastern Australia due to the recovery after the ionospheric depletion, as well as gravity waves following the eruption. All of this looks great, but was done in post-processing, and one might ask, what is the real advantage of real-time processing? And in order to answer that question, I will present the timeline on the right-hand side of this slide. From an event occurring, the atmospheric waves will reach the ionosphere with a delay between 8 and 40 minutes depending on the configuration. Traveling at the speed of light, the GNSS signals will reach the station almost instantaneously. At this point, a traditional GNSS station will buffer the data and release it typically the following day, but at earliest 25 minutes after receiving it. It is useful for post-processing, but far from ideal for natural hazards warning. Now, if we have a real-time station, the real-time data will be made available at the shortest possible latency, and TEC-based analysis can be produced minutes after receiving that data, and therefore minutes after the event. Deploying a new real-time GNSS station, or converting a traditional one into real-time, will yield the traditional benefits, positioning, seismic monitoring, etc., but will also grant access to real-time TEC products that can be used for natural hazard early warnings. And this is in fact what we're deploying at JPL with the Guardian system. which we define as a near real-time early warning system for natural hazards, focusing on the Pacific Ocean. Without getting into too many details about the architecture of the Guardian system, let me give this broad overview. The main block of interest here is the data collection block. We collect phase information from monitored stations as well as orbits, and from that we compute real-time TEC data for all the stations that we want to monitor. This data is then output to a public web interface that I will present in the next slide. Future work will include the development of a detection framework that will be able to automatically identify ionospheric disturbances, flag them on the public web interface, and eventually feeding them into an inversion framework which will be able to issue natural hazards warning. In the case of tsunamis, it will also be able to inform the users of inverted parameters, and for tsunamis, for example, the location, direction, speed, and wave height of the tsunami. I will now give a demonstration of the public web interface I was introducing earlier. This is what a user would have seen at noon UTC on the day of the Tonga eruption. A few key points to keep in mind is that the map is fully interactive, includes events in the USGS catalog, and that all of the stations that we monitor around the Pacific are selectable. Upon arriving on the website, the user would be able to see that an event has occurred with this red circle. Zooming in and selecting the region, the user would be able to click on the event, get more information about it, and select a nearby station. At this point, the list of satellites that this station has monitored is available. The user is able to select the satellites of interest and see the TEC data derived in real time for that station and those links. Zooming in and out gives an idea of the magnitude of the perturbations, and zooming in horizontally only will give you more details about the exact waveform. The user might be interested in checking the noise levels of those stations. Selecting a station that is further away from the event, one could be interested in also selecting a few links, and in this case, Baidu, GPS, and GLONASS to investigate the noise level, and clearly see that the perturbation seen near Tonga is significant. Another archive example would be the Haida-Gwaii earthquake and tsunami. This is what a user would have seen at 6 p.m. UTC on the day of the event, and selecting a station in Hawaii, we can clearly see the ionospheric signature on the right hand side here of the tsunami passing nearby. Of course, we have validated our near real-time stream against classically post-processed data. The RMS differences appear consistently below 0.1 TEC unit, which is more or less within the noise level that we observed during that day. The minor differences stem from data availability, effectively shortening arc length and thus affecting slightly the filtering. On this main plot here, I summarize the error metrics for a subset of stations that we monitor around the Pacific, from low magnetic latitudes to the left to high magnetic latitude to the right. For the northern hemisphere in black and the southern hemisphere in blue. We see that the different metrics stick to the noise level, which is highlighted with this gray rectangle. And I also show two example links from this dataset. The best link on the left-hand side clearly shows that the real-time stream is almost exactly equivalent to the post-processed data, and a relatively bad link shows that the arc length is at play and only a filtering issue is the cause of the difference here. Finally, I will report on the ionospheric coverage that the Guardian system allows in the Pacific Ocean. The maximum possibly covered area is 82% of the whole region. The current coverage that we have with all the stations in the system is about 60% of that maximum, and with addition that will be implemented soon, we will reach 64%. And we are also looking into strategically important locations around the Pacific to increase that coverage. The main conclusion and takeaway of this presentation is that GNSS data is readily available and can be used to monitor natural hazards in near real time. GNSS-based analysis have an excellent spatial coverage, especially with multi-GNSS tracking. And natural hazards such as tsunamis and volcanic eruptions can cause strong ionospheric perturbations that are easy to spot. Single GNSS ground stations are inexpensive to deploy and offer several crucial benefits, and even in remote locations, GNSS analysis could be achieved without a link to the internet. Thanks to the GPL GNSS stations, the Guardian system has the potential of achieving the near real-time high-rate monitoring of natural hazards. It has been validated against post-processing and will be made available soon. This concludes my presentation on this first use case, relying on satellite to ground data. I will give the floor to Mayra now, who will present a second use case, this time relying on satellite to satellite data.
Thank you, Allison, and thank you, Leo, for allowing me to be part of this presentation. The title, which is very long, is Transdisciplinary Applications of Global Navigation Satellite System Radio Occultations, or GNSS-RO, to Characterize Atmospheric Hazards and Model Systemic Risk. So basically, we're going to use radio occultation to better understand air quality in a fire event. I am Dr. Mayra Oyola-Merced. I'm currently an assistant professor at the University of Wisconsin-Madison. I must acknowledge, though, that the contents of this presentation was work that I performed while I was a scientist at the NASA Jet Propulsion Laboratory in Pasadena, California. And I want to take this opportunity to also acknowledge my JPL colleagues that provided valuable inputs and work into this presentation, which are Olga Verkhovyadova, and Allison Craddock. In 2020, California experienced the largest wildfire season ever recorded in the state's history, with nearly 10,000 fires burning 4% of the state's 100 million acres. We can see the impact of these fires in just one day. This is a NASA Terra satellite image that's capturing the smoke-engulfed state on the 24th of August, 2020. And we can see these different red dots over the satellite image. They represent individual fires. One of these fires was of particular importance, and it was known as the Complex Fire, which burned over the state of California from mid-August to early January 2021. So it took several months to be able to control this fire. The Complex Fire is known as the first gigafire, as the total area burned from this one single fire exceeded 1 million acres. So basically, it burnt an area larger than the state of Rhode Island. As a consequence, the air quality was deemed the worst on record, with more than 17 million people in the state of California and in adjacent states that were exposed to very unhealthy and hazardous air quality levels. And we'll talk a little bit about what that means within the context of this presentation soon. Similarly, this is not a problem that's intrinsic to California. We've seen other countries and regions battling the impacts of wildfires over the years, especially the increase in wildfire length and intensity. We saw it this summer in 2020 in Europe, and we continue to see it over China, Canada, Alaska, Russia, and of course, Australia. And we probably remember that very intense 2019-2020 wildfire Australian season that was all over the news, and it was very sad to see. Just as a reference, I want to show this plot on the right, which is using NASA's Mayra 2 reanalysis, which it shows black carbon concentration, which is a byproduct of fire activity, and it shows the anomalies of black carbon over 6 months, and compared. So this is 2020 compared to 20 years on record, and we can see how that year stood up compared to other years, specifically during August, September, and October. Now, let's talk about maximum daily PM2.5. Here, we're showing the maximum daily particulate matter 2.5. So basically small aerosols that can be basically absorbed by our lungs, and they can do permanent damage to humans and animals. This is a concentration over the state of California from the 1st of January 2010 until 31st December 2020. The data, it comes from Air Now. We are lucky enough in the United States that we have monitors in all over the states sampling air quality conditions. So there are some indices associated with different aerosol concentrations, and these indices are represented here by different color blocks. So that's what it's called an AQI, or quality index category. And they can go from green, which is good, all the way to dark maroon, which is hazardous. And we can see that between 2010 and 2020, California constantly hits unhealthy levels or worse on a daily basis. However, of particular impact is that 2020 fire season, which is clearly observed at the end of the time series. This is a problem because as the climate continues to warm, the fire season will continue to extend, and California, as well as any other country or region that's exposed to wildfire activity, will continue to increase their air quality risks. Now, I mentioned the word aerosol. Basically, aerosol encompasses particles that are suspended in the atmosphere, including PM2.5. Aerosols are not just stagnant in one point of space and time. They move, they transport, they move vertically, they move horizontally, and they react and interact with different constituents in the atmosphere. One of the most important interactions that aerosols have is that with water vapor. And I will use interchangeably water vapor, moisture, etc. in the presentation. But this is extremely important because it influences the size of the aerosol, the mass, how their chemical reactivity, and also their ability to create or destroy weather, because aerosols can act as something that's called cloud condensation nuclei, which basically ignites the cloud formation process. Now, water vapor is intrinsically important, and we do have some information about aerosol, and we have some information or long-term information information about water vapor in the atmosphere. However, it's very hard to find high level of aerosol information or events where there are high level of aerosols involved and accurate water vapor information, because most of our information comes from satellites, which is fantastic. They're great. They give us incredible temporal and spatial resolution. However, some of the satellites are mostly used for this type of observations, which are infrared. They're highly biased in the presence of aerosol. And this is particularly important in the lower atmosphere, which this is where you're going to find most of the aerosols and most of your water vapor is going to be at. And that region is called PBL, or planetary boundary layer. It's the first few kilometers in the atmosphere. So we have a problem. We don't have accurate information about water vapor interactions with aerosol, especially during events like a wildfire. Now, this is where radio occultation is great and can be heavily applied to solve this problem. So GNSS, as we know, it stands for Global Navigation Satellite Systems. We know that we use them for positioning, but they can also be used for weather. And this is an example using GNSS-RO, which basically is a technique that allows to utilize the GNSS satellite signal and capture it into another satellite that's positioned at a lower Earth orbit. And as this signal passes through the atmosphere, we're going to see some refraction. Atmospheric scientists like me can use that refraction to obtain information about temperature, water vapor, and other things in the atmosphere. They're great because even they are giving us or providing us information about temperature and moisture, but they're not restricted by the presence of aerosol. So they penetrate aerosol clouds and precipitation, meaning that this type of satellite is really good to sample fire conditions. Now, this comes with a caveat that the radio occultation does not sample aerosol concentration directly, but we could utilize information from aerosols combined with highly accurate temperature and moisture information from radio occultation to get a better idea about the weather conditions that can impact PM2.5 concentrations. Now, this is an example during that gigafire that I talked initially. Let's go back to it. So we obtained radio occultation profiles from a mission called Cosmic near the region of this fire. And as we can see here in the plot, we again go back into the different air quality levels, and we overimposed information about moisture and particulate matter concentration in the atmosphere. The green represents the moisture, the black represents the particulate matter. Before this record-breaking wildfire event, we can see that the daily maximum values of PM2.5 in California mostly stayed within moderate AQI levels. Before this day 75, and we can see here, this is the day where the fire started, we can see that there's a large spread between the moisture and the aerosol or the PM2.5 concentration. And as the fire starts, we can see that those moisture or specific humidity values will drop or dropped significantly, which create additional conditions for that could be conducive to additional fire activity. Eventually, we see that both the moisture and the aerosol or the PM2.5 concentration, as days go by, they drop both at the same time. Now, what does that mean? The behavior exhibited in the time series can be explained by understanding the nature of the aerosol. So once the fires have started, there's a process called oxidation due to the aerosol aging. So basically what happens is this aerosol or particle gets older, and it goes through time, they also become more hydrophilic. And what that means is that the aerosol attracts more water. And as it attracts more water, retains more water, these particles are going to grow in size to a point that they're too heavy to be suspended in the atmosphere, and a process called deposition occurs, which means they fall to the ground, which reduce both of the content and the concentration of the atmosphere. This is important because we can really understand in the remarkable influence that water vapor can have in the aerosol. And we can provide or better understand information about how long an event is going to last in the atmosphere, and even combined with other parameters such as wind, we can get a better information about where things are going or where air quality is going to be worsened or improved. Now, finally, I want to use radio occultation, example of radio occultation to show a different application, and which is completely related to fire activity. I mentioned before that as the atmosphere continues to warm, we're going to have more fire events. So a question would be, how has the atmosphere in California or in the region has warmed up over the past few years? Radio occultation is a technique that allows us to see that from the upper atmospheric perspective. What you see here is a trend, an upper atmospheric temperature trend at the 250 hectopascal level. So this what it means is at 11 kilometers from the surface up. This is a level that has been used for climate temperature trends before, and it has been documented in scientific literature. But what it does is suggest that radio occultation can be used to show these temperature increases. And what is showing is a robust increase of 0.4 Kelvin over the 17-year period leading to the fire season of 2020. There are a lot of implications. Just to wrap up, I just want to point out that as climate change contributes to unprecedented occurrences of severe wildfires, constituting significant threat to life, it will be important to understand how previously unused or underutilized technologies such as GNSS radio occultation may be applicable in transdisciplinary understanding of disaster risk, and how can these be applied to contribute towards sustainable goals, UN Sustainable Development Goals, as well as the goals of the Sendai framework. Finally, I just want to say, if you are interested in this topic, or if you have people in your organization that may be interested in this topic and other applications for weather and climate utilizing GNSS, not only GNSS radio occultation, but all of the different techniques, please reach to us. We have created a new pilot project in which we're trying to answer some of these questions in a very collaborative environment. Here you can see the links, or you can email me to Oyola-Merced@wisc.edu for more questions on this presentation or about the pilot project. Once again, thank you so much for allowing me to present, and I hope you have a great rest of your day.